Now go ahead.
Okay, I'll start again. So I'll be presenting my PhD proposal defense on the topic of strategic movement and moving target defense. The chair for the committee is Dr. Subbarao Kamampati, and the other committee members are Dr. Tiffany Bao, Dr. Dijan Huang, and Dr. Guliang Suen. So to start off, let us first talk about what is the present scenario of most cyber systems that is out there. The basic idea is that you have a single system deployed, and essentially an attacker can probe the system, spend reconnaissance effort in finding out what the system has, and then spend time designing an attack, or if an attack is already available, using it to exploit the system. Now, this notion also generalizes to newer attack surfaces that have become more ubiquitous in the present day. For example, machine learning has been used in, say, autonomous vehicles, facial recognition, and henceforth, you could actually use the same kind of a paradigm where your machine learning system is application deployed, and the attacker, instead of trying to find vulnerabilities in code, is trying to find vulnerabilities in the machine learner's representations to actually attack the system. An alternative notion to this static security where you have a single configuration deployed is this idea of moving target defense. So the idea of moving target defense is basically, instead of having a single application, you have multiple configurations that support the single application. And the idea is that an attacker who has, say, spent reconnaissance effort in finding out what the system might be, at the time of attack, when it tries to attack using the green arrow for the green configuration, might encounter a different configuration and henceforth not succeed at the attack time. Now, it seems that if you have moving target defense over your existing notions of cybersecurity, it should be the best defense overall. Because you could use all your vulnerability patching techniques, your intrusion detections, your intrusion prevention systems, and on top of it, deploy a moving target defense, which is kind of a defense in depth solution, where you will make sure that the attacker only probabilistically succeeds in being successful at an exploit. And so this should seem like the best notion of security. But there are a few challenges to this. And if we take a more critical view as to what those challenges are, we will see that a moving target defense entails switching costs. So basically, at any point, if you have a deployed configuration and you want to shift this configuration to another one, you might have latency impacts, you might have downtime, and things like that. The second problem also is that each of these different configurations might have asymmetric performance impacts, which is basically saying that one of your deployed configurations might provide you response in a smaller amount of time, while another might take a much longer amount of time. And then there is also this concern that these different configurations that you have deployed, if there exists a single attack that can cripple all of these configurations, then basically you haven't gained anything by doing moving target defense. And we will see this more in the case of machine learning security, the third one, where it's very well known that the attacks that you generally come up with is transferable to other networks. So what this thesis kind of tries to look at is that it tries to say that when you are designing any moving target defense system, you basically have to consider the configuration set that you're moving, when you're supposed to move them, and how you're supposed to move them. And a notion that was kind of very popular before this thesis came about was that people use Naïve randomization strategies to actually move the system, which says that at the time of movement, just with equal probability, decide how you're going to move from this particular configuration to what is the next configuration that you should move to. And we will argue in this thesis that this is not really good either for performance nor for security. And we will suggest that if you want to do this right, you should think in terms of a game theoretic model. And this game theory is kind of the notion of an AI agent who is trying to move. And this is, we will use some AI methods to actually help this notion of moving target defense in cybersecurity. So this is a kind of AI for security, kind of a thesis contribution. And the basic goal is that we'll act as the Shifu in Kung Fu Panda, and we'll teach the panda how it should move between the different configurations to optimize for both security and performance. And we will also consider a rational attacker who knows that the panda knows how to move well, and in that context, how they should design their attacks, right? So this thesis will try to look at three different sets of contributions. One which kind of tries to address the problem of switching costs that arise in moving target defense and how game theoretic formulations can address that. The second is asymmetric performance impacts of the deployed configurations and how you can account for those while you design your movement strategies. And the third is what happens when a particular attack can cripple different configurations of a moving target defense to different extents. And how I also view this as, it's kind of two parts to this. One is we use some AI methods in game theory for coming up with strategies, and that's part of AI for security. On the other hand, we also use the notion of moving target defense, which has been prevalent in cybersecurity, for machine learning security, which is kind of the AI attack surface that you have. I have also been fortunate to be a part of the AI Sec workshop at IBM AI Week last year. And there is also a lot of active work in security for AI, where they see what kind of different attacks are possible on machine learning models and what kind of defenses can you get inspired from in cybersecurity for AI. So before we start diving deeper into the works that I'm going to talk about, first let me give you a very brief overview of some of the game theoretic terminologies that I will be using throughout the presentation. So for the entire presentation, I will be using two-player games, where two players for me would essentially be a defender and an attacker. Also, when I talk about pure strategies, I essentially imply that, for example, the defender has two pure strategies or two actions. One is U, one is D. When I talk about, and in this case, the attacker has L and R. When I talk about mixed strategies, I'm talking about probability distribution over the action set. So for example, 0.6, 0.4 could be a possible mixed strategy for the defender, but you could have other values as well. Also, I will be looking at the notion of general sum games as opposed to zero sum or constant sum games. Basically, what that means is the reward structure for the two players might not be a simple one where I say that the reward for the attacker plus the reward for the defender sums up to a constant value or sums up to zero in the case of zero sum games, but it can be any arbitrary value. So that's that. Also, predominantly, I'll be talking about this notion of Stackelberg equilibria, which means that one of the player has an advantage of actually giving their strategy upfront, which is say 0.6, 0.4. So essentially, our threat model will assume that the attacker knows that the defender is going to move between different or choose between different actions with this probability. And based on that, they are going to decide what is the attack strategy that they should use. And so we've used the notion of Stackelberg equilibria. We will also consider normal form games. There's a lot of details as to why I'm considering normal form games as opposed to extensive form games when it comes to Stackelberg equilibria. And basically, one of the reasons is that if you start considering extensive forms, then the branching factor of the tree actually becomes infinite. But I won't get into the details of that one here. And in one of the sections, I will talk about stochastic games, which essentially says that you have some state in your game, and if attacker takes some action, the defender takes some actions and the attacker takes some action, then you can land up in different states. And so that is the notion of stochastic games we will talk about in one of the works. So with that, let me first talk about this notion of addressing switching costs. The setup for this setting is that we have MTD configurations which are web application configurations. It's full stack web application configurations. We will switch at a constant time period. Basically, after every time period T, we'll consider a switch action. And what the movement strategy needs to account for is the switching cost associated with the system, and the security of the system. So let's start with this small example where the defender has two possible configurations that the system can be in. One is it uses PHP code and MySQL database server. The other one uses Python code and uses PostgreSQL server. And a very naive idea of coming up with a strategy could be to say use a uniform random strategy, which says pick any of these configurations at every switch point of time. Whenever you're going to do a switch, pick either of these strategy with a probability of 0.5. Now, there are quite a few problems to it. One is obviously that, let's say this configuration has a response time of 2 seconds, whereas this configuration has a response time of 0.5 seconds for any web application request that comes in. So you would ideally switch to this costlier configuration with equal probability. So that's one problem. The second is it might just be that there is one very critical attack on Postgres MySQL that can cripple the configuration, but you would switch to this configuration with equal probability. And third is, at any point of time t, you will have 50% chance of switching, basically not staying in the same configuration, but switching to the other, at which point you will also incur high switching costs. And to address this, now what we are going to consider is how we can model this as a game theoretic problem. To do that, let me also introduce a few notations along the way. One is to represent a defender's mix strategy. I will use the vector x. So basically, if I say that a defender mix strategy is 0.6 and 0.4, then basically your x1 is 0.6 and your x2 is 0.4, right? So that's that. For the attacker, the modeling is a little bit more involved. So the first thing is, how do we come up with the actions of an attacker? And to do that, what we do is we mine the common vulnerabilities and exposures in the National Vulnerability Database. And for each of these CVEs, we have a list of technologies that it can affect. And we can also find out an expertise code that is needed to actually run these exploits on a system. And we are going to consider an action, a part of an attacker's arsenal, if it satisfies a few requirements. Now, what are these requirements? So the first part is to recognize that you cannot consider a single attacker to have different capabilities. For example, you might have an attacker who is so powerful as a nation state, which can use any difficult or exploits that need a lot of expertise, lot of resources, versus you might have attackers who are basically script kiddies. And at that point, so you should ask yourself this question, that if you know that your system can only be attacked by script kiddies because maybe it doesn't have information that a nation state might be interested in, then why should you choose a very aggressive defense strategy against it? And so to capture this notion, we allow the defender to define a formal notion of attacker types. And this attacker type is defined by ID or a name. And it says that what technologies the attacker has expertise in, and you can have multiple technologies in this set, and what is the expertise that is associated with a particular technology that the attacker has. And once you define this set of attackers, we can leverage the list of technologies it can affect and the list of technologies the attacker has expertise in, and the expertise of the attacker and the expertise that is needed to exploit the CV and the expertise of the attacker to pair up attack actions to attacker types. So we will denote each type with the superscript theta, and a Q theta vector essentially represents a mixed strategy of the attacker. So again, in this case, if you said that the attacker is going to choose this action with 0.6, 0.4, then this represents 0.6, 0.4, right? So that's that. Now comes, how can we define a reward structure for this normal form game? Now the reward value structure is very simple. It says that if there is an attack that can exploit a vulnerability in a particular configuration, then the attacker's reward is a positive reward. Similarly, if the attack can exploit a vulnerability in the configuration C that was deployed by the defender. Sorry, I think Dr. Golyangshu has a question, so I guess I will go to that. Let me see. Oh, great.
He should be able to unmute himself, right?
Oh, yeah, Dr. Shui, I think you had a question, so.
Yes, can you hear me?
Yeah, I can.
Can you hear me?
Yes, I can.
Yeah, yeah.
Just a quick question.
Yes.
Is the defender the leader in this game?
Yes, it is.
That's my question. Yeah.
Yes, it is. Basically, and the assumption is made based on the fact that in any cyber system, a defender will actually have to deploy a system, and the attacker can spend some reconnaissance effort in figuring out what the strategy of the defender might be. So a stronger threat model in this case would assume that the defender plays as the leader, and the attacker knows the committed strategy of the defender. Okay, so I'll move on. So the reward structure for the game is kind of simple. If an attacker can exploit a vulnerability in a deployed configuration C, then the attacker gets a positive reward, defender gets a negative reward. These might not be the same, and we will see why that is the case in the next slide. And if it can't, then the attacker has some negative reward for spending effort in trying to do this attack, but not gaining anything from it. The defender could either gain some positive thing if the attack is detected, or either not gain anything if it has just successfully prevented it and it was its job to prevent it. And how do we come up with these reward values? We saw what the structure is, but how do we come up with these values? And to come up with these values, we leverage the common vulnerability scoring system. So basically, it's a metric that is associated with CVEs in the National Vulnerability Database. And at a high level, you can divide this metric into two scores. One is the impact score of the attack, and the second is the exploitability score, which kind of tries to capture what is the amount of expertise needed to actually use this exploit. And there is also this notion of a base score, which kind of tries to combine both of them. So in the case of the defender and the attacker's reward values, we use the impact score for the defender, which says that if the attacker was able to successfully exploit the system, what is the impact that the defender is going to have? And for the attacker, we use the base score because we want to capture this notion that if there, say, exists an attack which has very high impact, but also needs a lot of expertise and a lot of resources to perform, then the reward is a little low. Otherwise, if say this is high versus say this is high and this is low, then that should be a more attractive attack for the attacker. And so using that, we can form a normal sum game for our problem. And now having this normal sum game, what is the objective that we want to maximize to find a defender's strategy? And the idea is that you want to maximize the defender's reward, knowing that the attacker is also going to maximize their reward, because this is a general sum game. So instead of a max min or a min max, we can think of this as a max max strategy for the defender. And to do that, the main objective that you're trying to optimize is the expected reward of the defender. So what this is saying is that you have certain probability with which an attacker type theta might exist in the world. With a certain probability, a defender might select the configuration C, and the attacker type theta might select the configuration A. And the defender will get a reward of this value if this attacker theta plays, if it chooses the configuration C, and the attacker chooses the attack action A. So basically, this is the expected reward of the defender that you're trying to maximize. Now, notice that you also have to account for the fact that the attacker is also trying to maximize their reward in this game. And to capture that, we can actually put this as a set of constraint in the optimization problem that I'm describing. Without going into a lot of the details, let me do a quick overview how this particular constraint tries to capture the attacker's maximization problem. So basically what it says is that actually instead of C, there should have been reward of the attacker given IJ, but so in this case, the attacker knows the XI values, which is the defender's strategy, which is kind of the assumption we made for the Stackelberg setting. And it has a reward associated if the defender picks XI and QJ. So the attacker is basically trying to maximize its own expected reward given a defender strategy. And if you consider the dual problem of this setting, you would get the problem on the right. And then if you use the dual, you use the primal feasibility constraints, you use the dual feasibility constraints, and you use the complementary slackness constraint, then you will be actually able to capture the attacker's maximization problem in this setting. I won't go into the details due to interest of time, but details are kind of available in our paper and will also be there in our thesis. So for now, what I have mostly talked is that I've told you how you can ensure security, how you can come up with a defender's mixed strategy such that the security of your system is maximum. But at the start of the presentation in this section, I said that I would also want to look at the switching costs. And in this case, for web stacks, shifting from one database to the other, or changing from one coding language to the other, reallocating requests on the load balancer from one system to the other, can actually incur costs of latency or downtime. And so you want to capture this cost when you're trying to come up with the defender's mixed strategy. And one way to do this is kind of consider the expected cost, which says that what is the probability that a defender would find itself in the configuration I? What is the probability that given in I, it would switch to configuration J? And if the cost of switching from I to J is denoted as Kij, then what is the expected cost of switching for all possible switches that you can have? And that kind of tries to capture this notion of switching costs into this optimization problem. Now, this bilinear term also makes the solution of this LP a little inefficient. And hence, to aid that, what we do is we use the McCormick envelopes, which says that this variable Wij captures the notion of this mixed, well, one-step mixed strategy. Ideally, you should note that there is a Markovian assumption we are making here, which says that even if the defender had configuration, say xi-1, xi-2, before the xi configuration it is deploying, we are not going to consider the probabilities of these because we are saying that that shouldn't affect the switching cost. If you're switching from configuration I to J, you shouldn't care about what is the history of configurations that you have been through. And henceforth, this variable Wij captures this one-step switching costs. And then we use the McCormick envelope constraints on this in this optimization problem to actually come up with a solution for the defender's mixed strategy. Now, having done that, we also perform some experiments on a small code web application code base, which had 4 possible configurations. While I was using a 2 configuration case for the entire example, in the paper, you'll see that we use a 4 configuration of the web application scenario for MTD. And we have, in this table, we denote the switching costs. As you will see that switching between both coding languages and the database server incurs the highest cost. And this is normalized between 0 and 10 because CVSS scores are between 0 and 10. We also, if you did notice, we also allow for a tunable parameter alpha that says you can decide how much to prioritize for switching costs and how much to prioritize for security. And in the switching cost matrix, we did assume it to be a symmetrical one, but it doesn't really have to be a symmetrical one. And for whatever asymmetric matrix that you might have, we can still solve the optimization problem that we described. And to find the attack actions for each attacker type, we did a mining of the CVSS NVD database for CVEs, and we use the method of associating the expertise and technologies required in an attack to the technology and expertise of attackers to associate attack actions. And the highest number of attack actions was for the database attacker, which had around 269 attack actions. So with that, when you solve the optimization problem, the strategy that you would come up with for this Bayesian stackable game is that it says that be in the configurations only with the PostgreSQL server and do not switch to any of the configuration that has the SQL server. Now, instead, if you were using the uniform random strategy, which was kind of the state of art before this paper, you would actually switch to these with 0.25. And basically what this shows is that you would neither gain anything in security. Moreover, you would impact your cost of switching if you chose to use a naive strategy such as the URs. This is also kind of indicated by the defender rewards. And it also kind of shows that the attack actions for the different attackers that they should use if they want to get the highest reward in the case that you are playing these strategies. So in this work, we also show a few other kind of results. One is that we show that if your assumption about the attacker types or the probability over the attacker types who you will encounter in the real world changes, then the MTD strategy turns out to be more robust than the uniform random strategy. We also design a metric for this, and we show that this is the case. We also show that in case of fixing vulnerabilities, if you are, say, deployed in a static security setting where you have a single configuration and somebody asks you which are the key vulnerabilities I should fix, that's an easy question to answer. But as soon as you get into this setting of MTD and you start reasoning over the attacker types and the mixed strategies of which configuration is going to be deployed, then this problem of finding the top key vulnerabilities to fix becomes a hard problem. Well, not hard in the sense of we haven't actually defined NP hardness or any complexity class over it, but we show that this is not as easy a problem as doing it in the case of the static setting. And we also note a few other observations where we see that existing stackable equilibrium solvers that have a corresponding MILP version, but which lands up in increasing the number of variables by a significant amount, becomes a little slower when you have as many attack actions as we do in the cybersecurity setup. Now I will move into addressing the asymmetric impact of performance in an MTD system, and I will look at results from one of our works that was published in GameSec 19. And in this case, the configuration set for the MTD is an IDS placement setting where you can have different IDS placement configurations. You have a constant time period. So after every time period T, the placement is going to switch in the cloud network system. And third is we are going to account for the asymmetric performance impact for each of the different configurations. And we'll also account for the fact that the attacker might have a multi-step plan in attacking your system as opposed to just having single attack actions. And so the scenario we consider is basically, let's say you have a cloud network system and you have a huge amount of host and network-based intrusion systems that you can deploy on the system. Now, we and earlier works have also shown that if you choose to deploy all such IDS systems into your cloud, then it can impact your performance metrics, which could either be the bandwidth, the CPU usage on your virtual machines, and things like this. And so the question is, can we get the not exactly the same amount, but a decent amount of security while not compromising on this performance by placing a subset of these IDS systems into the cloud network? And if you have been paying attention to the presentation, the answer is a yes. And the answer to that is we can use moving target effects. So before I get into the crux of it, a few of the limitations of the previous work that we kind of also address in this contribution is that in stackable security games, which have been very popular in popularizing the notion of stackable equilibria, is that they assume that attacks are always successfully detected so they are either caught or they are always successful with 100% accuracy. And we kind of try to relax that assumption. The second is if you allow for multi-stage attacks where the attacker can come up with attack paths, then you can basically allow for an infinite set of pure strategies because the attacker could choose loopy paths in your system, essentially having an infinite number of pure strategies. And the third is some of the previous works assume that the attacker can attack any node in the cloud network, whether it is an internal node which is very deep-rooted or in a demilitarized zone versus it's at the juncture between the public interface and the cloud networking system. So to consider this IDS problem placement and formalize this, we use a Markov game model. We can later discuss that this could have also been considered as a partial observable, but that would have impacted scalability, and hence we stick to a Markov game model. So let me first start by defining a Markov game model. So a Markov game model kind of has a set of states, which are finite states, and this set is finite for the game. We assume that two players, so in our case, this is a two-player Markov game. We have two players who have attack action sets A1 and A2, and this for the defender, this for the attacker. And then we have a transition function, which says that if you were in one of the states of the game and your defender chose the action A1, your attacker chose the action A2, then you would land up in the state S dash of the game with a certain probability. So this is a probability distribution over the state space given your state and the action pairs of the players. You also have ideally two reward definitions or two reward matrices. One is for the attacker, one is for the defender. And this is said that if you were in the game state S and the players chose to play A1 and A2 respectively, then what is the reward that you would get because of this? And finally, we have a discount factor. Now, this discount factor could ideally be different for the defender and the attacker, but for this work, we kind of assume that it's the same. So that's the definition of general sum Markov games we are going to go with. Now the question is, we said that we started with cloud networks, and now we are talking about a Markov game. So clearly there has to be some kind of mapping that has to take us from this sample cloud network scenario to a fully formed Markov game. And to do this, we basically leverage attack graphs. Now notice that the problem of going from a simple cloud network scenario to an attack graph is also a complex one, and there are people in this proposal who have worked on it, but I will not spend time on that because this is beyond the scope of this work. So we will assume that when you have a cloud network scenario, you can generate an attack graph corresponding to it. Now, once you have the attack graph, you can use the states of this attack graph, which say that where the attacker might be and what are the privileges that it might have as the states of your Markov game. For the actions, you can use the attack actions in your attack graph and also pair up the attack actions of your defender. So for state S1, ideally the defender could also choose to monitor for LDAP vulnerabilities, and the attacker could choose to say not exploit anything. And so basically you would have 4 attack actions for this state, but for brevity, I'm just going to show one attack action in this context. Similarly for S2, here, the defender is choosing to monitor vulnerabilities on the web server, and the attacker will choose to exploit the web server using an anomalous traffic packet. So that's how we are going to define actions for this game, which can be kind of taken from the attack graph and the possible defender actions that are allowed for this IDS deployment setting. And then we talk about what are the transitions in this game. And basically the transitions can be used to represent two kinds of things. For example, let's say that a buffer overflow where you're not sure about exactly by how many knobs you have to insert to actually make it work or not. In that case, there is some probability of the attack succeeding and the attacker moving to the next stage. Otherwise, with some probability, the attacker will still remain in the same stage and try to again use this buffer overflow attack. So that's one notion we can capture. A second notion that we can capture with this transition is that in modern day cyber systems, there's a lot of use of machine learning in trying to detect anomalous traffic packets. But again, as we know that the accuracy is not always 100%, and henceforth, there might be cases where you are not able to detect this attack 5% of the time, and the attacker gets to move to the next state of your system. Or if you are able to, then you will actually keep the attacker in the same state.
A clarification question, so that could you
Yes.
just say again, what do you define, how do you define the state?
All right, so in this case, the state is defined by the states of the attack graph. So basically, it says that the attacker might be located in the LDAP server and might have a privilege of being a user, and this is your one state. So the attacks, so the states of the attack graph kind of give you the states of your Markov game.
Okay, thanks.
I also have a follow-up question.
Right.
Given the strategy space of the two players, what is the state space? So is this number of states going to be exponential?
Oh, no.
The number of strategies of player 1 and number of strategies of player 2?
Right.
Or is that a polynomial?
So in this case, okay, firstly, we assume a finite state space that's obviously there. And in our case, to be honest, the state space could be exponential, but for the examples that we have looked at, and also a kind of simulation scenario that we have looked at, the state space is, I would say, polynomial times the attack action. It's basically, it could be exponential if your attack graph has an exponential number of states that the attacker could be in.
Okay, thank you.
So having defined how we design the states, the actions, the transitions, we now move into the reward modeling part of it. And in this case, a notion why we don't have a zero-sum game is basically because for each of the IDS deployment, there is a performance cost or a quality of service cost that the defender will have to face. So in this example, it kind of shows that even though the attacker did not use any attack, just because the defender chose to deploy an FTP-based IDS system, it is going to have to incur some performance impact, right? So that's what it denotes. And the ideal notion is that the attacker shouldn't really care about what is the cost being incurred by a cloud service provider or a defender when it is considering deploy IDS system. And hence that kind of takes out the zero-sum notion of the game. Now to find these values of -2 that we have here, previous works have kind of thought of using centrality measures, which kind of says that if I were to place an IDS system, which is a host-based or a network-based system on this link or on this node, then I am going to incur impact proportional to the centrality measure of this node, because this node is going to be in the path between so many start and end nodes and stuff like that. But in our case, we kind of ran mininet simulations to actually come up with these values, which I think approximates it better than some of the existing works. And now once we have this Markov game set up, we can actually use what is generally known as the Bellman heritage, even for multi-agent games, is that basically we have this iterative procedure of calculating the Q values and then using the Q values to update the value function. Now, in case of a single player, you would say that the value is just the max of the Q values of the states and actions, value of the state. In the case of multi-agent systems, you could, so if this was a zero-sum game, then you could just consider, say, a min-max strategy, sorry, a max-min strategy over the set of Q values for the states and the different, sorry, Q values for the states, actions of the players, stuff like that. But a more general notion that we can use is the notion of equilibrium, which kind of says that your value functions for the state is calculated by calculating some equilibria of the Q value functions of the different players that you have here, which kind of forms the matrix normal form games of this Markov game. And in this case, we can consider two different kinds of threat models. One is where the attacker has no idea about the defender's placement strategy and they both play simultaneously, which is a Nash equilibrium case. And the other is a stronger threat model where we say that the attacker, say, somehow has found out the defender's placement strategy over time, over reconnaissance actions and stuff like that. And now they're going to decide what attack actions they can take. And henceforth, by solving this kind of a Bellman update-ish algorithm for the multi-agent case, you can find the optimal strategies for the defender and the rational attacker as well. Now for the results, we compare our strategy with two existing strategies. One is the uniform random strategy, which says that in any state, if the defender has X actions or N monitoring actions, then they can select one out of that N at random, which is placing equal probability on any of those. The other is the notion of a min-max strategy, where you say that the defender forgets the performance costs and it's going to only consider the impact that the attacker might have on the system, and you could then formulate this as a zero-sum Markov game and you could come up with a strategy for that. And what we see when we compare with these two strategies and the notion of Nash and the strong stackable equilibria is that for all the states except this one, which is kind of a terminal state with just one action, the notions of Nash and strong stackable equilibria is better than the existing methods. Now, one very interesting case we also noticed here was that the Nash and the stackable equilibrium in all the states kind of give you the same value. And when we look back at the Markov game setup, we realized that there was a particular structure over the pure strategy set of the defender that for this context of the game said that any strong stackable equilibria that you find is going to be a subset of the Nash, and henceforth they're going to yield the same values. Now, there's a more formal proof in the thesis and also the paper that we worked on for this, but I won't discuss that for the interest of time. We also noticed an interesting kind of aspect from the cybersecurity setting, which kind of said that if you are in states which are further away from the goal, then with some non-zero probability, you can sometimes choose not to monitor for an attack. And on the other hand, if you are in states which are very close to the goal, then you should always place full probability in monitoring. So in this case, basically, there is kind of no moving target defense.
So Sailik, I have a question.
Yes.
So the notion of a closer and a further away, how do you define that? By the number of transitions, number of movements, or by the utility function?
Right. So in this case, the answer is by the utility function. So we assume that a Markov game has a terminal state, and that is also denoted as the goal state of the attack graph. So attack graph's a goal state, which kind of says that your attacker has gained root privilege on your FTP server, and that kind of is the most lethal stage that you don't want to get into. And we use utility values to actually define this terminal or absorbing state in Markov games.
Okay, just a point in here. Essentially, you have a function. The utility is a function of, for example, the variable. If given x1, x2, if fx1 and fx2 are very close to each other, it does not always mean that x1 and x2 are very close to each other.
Right. Okay. Right. So that is true. Maybe I think I couldn't get one point across.
No, just a notion, a note for the future. Okay, so you can continue. Yeah.
Right. Okay. Yeah, but sure. I will. Just a very small thing. Ideally, the case is that this is S1, this is S2, and ideally there is no transition, say, from going from S1 to the final terminal state of S. I call it S0, but let's call it SG for the goal. And you would at least have to take multiple steps to actually reach this goal. And henceforth, how I'm denoting this notion of far away from the goal state is basically by the number of actions that the attacker would have to take to reach this. I define that you have reached a goal state using a utility value, but how far you're from this goal state is defined as the number of attack steps that you might have to take.
Okay, thank you.
So we also kind of used a star network setup that was kind of used in the Western region cybersecurity defense competition, and we kind of deployed the VMs that were provided for that competition in a small mininet setup. We used OpenVAS vulnerability scanning tools. So we used a centralized controlling system like SDN to actually find out the vulnerabilities that exist in the system. That's the list of vulnerabilities that exist. Then we use the centralized controller to come up with a Markov game strategy for this setting. And then we actually implement this by using enable disable scripts that enable and disable the IDS, the different host and network IDS systems at every time period T. So we have some results on this, and we show that in the simulation setting, the advantage of using a strong stackable equilibrium strategy is much more than using, say, something like a uniform random strategy. With that, now let's talk about the setting where you might have attacks which can have or which can cripple multiple of your MTD configurations at the same time. In the case of cybersecurity, this is generally not a huge concern because each of the exploits are specifically crafted to technologies, even to the version number of technologies, and it wouldn't work for a different version. And so in the case of existing cyber surfaces, this is not a huge concern, but in the context of machine learning security, as we will see, that this becomes a concern. And the question is, can MTD still work when this is there? And if so, how much of it do we need? So we'll talk about this. Before getting into the notion of MTD for machine learning surface shifting, let's talk about the threat model that exists in this kind of a novel attack surface. So the threat model that has been mostly popular, but it's not the only one, is essentially this norm-based noise, where you're saying that you have this input I, and you have an attacker who is crafting a perturbation or a noise epsilon that is bounded within some p norm of this input space. So basically, this is the pixel space. And when you add this perturbation into your image, it results in this new image I dash, which to a human would look like a school bus, which the original image was as. But to a neural network, this would look like a completely different class with very high confidence. And in this case, an ostrich. So that's the kind of attacks that we'll be considering. There is a lot of attacks about how you can generate real world perturbation, adversarial patches, and I refer you to the survey to get an overview of it. But for this work, we'll only consider norm-based attacks, which have been very famous in the last few years. And the existing defenses, to be honest, I'll keep this short because only one of the defenses really works well, and that's the notion of adversarial training. So the ideal training for any machine learning or a neural network classifier is that given X, given Y, which is a supervised classification setting, you want to find a set of parameters that minimize your loss function. Now, the notion of adversarial setting is that when an attacker tries to find an epsilon, it's trying to maximize your loss by finding this epsilon. And you, on the other hand, are trying to minimize over it, which is basically including these perturb samples in your training set and retraining your parameters, which basically says that you're trying to minimize over the attacker's loss function. Now, obviously, this has some problem because once you do this, your network might be more aligned to classifying the adversarial inputs correctly, but might not be classifying your original benign test samples well. And so ideally, you can think of this as trading off between your original classification objective of classifying benign test examples and classifying attack examples by using some sort of a measure. And we will try to actually address this concern in this work. So the notion that we have at a very simplistic level is saying that we're going to use moving target. What this means is that you will have an ensemble of neural networks, in this case 3, blue, green, and gray. And an attacker is going to come up with an attack knowing that you are using an ensemble and you might be using a randomized way of classification. So let's say if the attacker chooses an attack action green epsilon, which is designed for this network, at test time when it inputs it, and you have a probabilistic selection strategy, and you pick up a blue network, this blue network is not vulnerable to the green perturbation that the attacker crafted, and henceforth you classify it as the correct class 0. So that's the notion we are going for. And what we're going to do is we are going to try to find a strategy for this moving target defense for switching at testing. Now, one thing, if you are familiar with the literature in neural networks, is that it has been shown that an attack crafted for a particular neural network can oftentimes cripple the other neural network. So an attack crafted for this might be able to actually cripple this and this too. And so the question is, if that is the case, then what's the point of doing a moving target defense? Because it will cripple all the networks. So no matter what you select, you're still going to be vulnerable. And we formalize this notion in our work by a notion called differential immunity, which says that if you have no differential immunity, then you will have a particular attack action cripple all your defenses to almost 0% accuracy in the existence of that attack. On the other hand, if you have a differential immunity of 1, it would ideally say that there is no attack that can cripple more, or that has at least one network it cannot cripple at all. So basically, if you have high differential immunity, then there is some reason why you would want to do moving target defense, as opposed to if you have no differential immunity, you should ideally just give up. And we will see that in all the empirical evaluations across data set, for neural networks, the differential immunity is never 1, which is not a very happy news, but the good part is it is neither 0. And henceforth, it dwells in this realm or the spectrum of 0 to 1. And with that, you can actually gain some advantages in robustness. So what are we trying to do here? Now, what we are trying to do here is we are saying that we are going to optimize the loss for adversarial examples. We are also going to optimize the loss for the original test examples, and we are going to trade that off using some parameter alpha. And what we're going to do is we're going to find a strategy of how we select each of the pure strategies for the defender. So in this case, it's again, the defender has three strategies or three pure strategies of selecting one of the networks at test time. And the user is divided into two parts. So this is again a Bayesian game setting where you say that you believe that a sample sent by a legitimate user is a sample is sent by a legitimate user with 0.95% probability or an adversarial user with 0.05. And ideally, the reward functions are that if it's a legitimate user, then the classification accuracy is both your rewards. So you get high rewards by classifying it correctly. The legitimate user is happier because it gets the correct classification. For the adversarial user, it's a zero-sum game. And in this setting, what we are trying to find is we are trying to find these pure strategies, which is P1, P2, and P3 over the networks theta1, theta2, and theta3, such that you can jointly reduce the loss function when you know that the attacker is going to maximize this loss function using that attack. And you can use the same kind of Sackleberg equilibrium solvers we discussed earlier. Now, in the case of neural networks, how good or bad is it? So what we did was we had three different data sets. One is the MNIST data set, one is the fashion MNIST data set, and the other is the ImageNet data set. And we use different attacks, such as the fast gradient methods, the deep fool methods, the projected gradient method, which is the strongest attack right now, and also the set of universal perturbations. And we saw that in each of these cases, we get an accuracy improvement of around 24%, 22%, and approximately 21% for ImageNet. So that's pretty good, given that state-of-the-art existing methods can go up to a maximum of 45%, but also the case that in all of these classification challenges, even an improvement of 3 or 4% accuracy has been kind of made somebody a leader and the state-of-the-art. Now, a notion that I'll come back to, which I discussed at the start of the presentation, is that this notion of moving target defense can always be used as a defense in depth solution, which means that you could still use your existing notions of how you deal with exploits and vulnerabilities plus moving target defense. And so we did that in the case of neural networks. So we said now the defenders ensemble comprises of not only networks that are trained on the original data set, but also ones that are trained on the adversarial example. So you have the ensemble adversarially trained. Basically, the notion of ensemble adversarial training says that you have trained your multi-layered perceptron with attack images that were crafted for CNN and HRNN as well to be immune to those. And so if you do this, you will see that the accuracy gain in our case is almost 50%, or rather almost 51%. And I think this is almost close to the state of the art, if not better than it, which is the projected gradient descent with ensemble adversarial training. And we used only the fast gradient method for ensemble adversarial training. I'm guessing that if we use projected gradient descent with ensemble adversarial training plus MTD, we are actually going to also improve or be the best out there. So one question that I kind of have swept under the rug is that I have been talking about attacks that are crafted for these individual networks, but not really for a randomized ensemble, something that is randomizing at runtime. And so the question comes that could you craft an attack that seeks to attack this entire thing at a single time, as opposed to trying to design attacks for each of the individual classification systems? And the answer is yes. So the notion that we use to craft these kind of universal attacks for the stochastic ensemble is the notion of black box attack. So what black box attack is, it's basically a chosen plaintext ciphertext attack. So what it says is that immaterial of the networks that you have and how you're doing randomization, I'm going to provide you with a set of inputs, and you're going to provide me with the set of outputs that your network gives for these inputs. And what I'm going to do is I'm going to use this as my X, this as my Y, and I'm going to train a surrogate model, which is a smaller neural network model with this XY training set. And after I do that, I'm going to develop an attack for this n dash. So I will have an attack action for this n dash, and I will see if this generalizes to this existing MTD ensemble. So if I can use this attack against this MTD ensemble altogether. And when we do that, we see that this attack action is not even as strong as some of the white box attack, which basically says that if you were to include this in your normal form game, it would be strictly dominated by at least one of the white box attacks, and henceforth the attacker should have no incentive to choose this. And so basically this kind of a universal attack crafted using black box attack doesn't work. Now, I'm hoping that at some point of time in the future, people might think of newer methods to come up with attacks against a randomized classifier than what exists today. But for the ones that exist today, we couldn't get it to be better than the threat model that we had already considered. A last notion that I would also discuss is this notion of how does this differential immunity value relate to the gain that you might see in robustness? And as you might expect, that higher differential immunity values will give you higher gains in robustness. And here there's a bit of a apple to orange comparison, because ImageNet has kind of 1,000 classes that it can classify to, and henceforth the random classification would look something like this, versus for any of the other data sets, a random classification would look like something like this. And henceforth, we can think of including the notion of how many classes you want to classify to into the differential immunity measure, but for now we don't have that. But we generally see that for these three cases, if you increase the differential immunity, then you'll get an increase in the accuracy gains. So that's that. And one of the other interesting questions that people have kind of started looking at after our paper is this: is there a way to obtain these theta I values or these different networks for your ensemble that are differentially immune at the start? And basically, if you want to do that, one of the notions that has been looked at by one of the papers in 2000, well, I think it got published later, but on arXiv in 2018, right after our arXiv version, was that they said that if you have the output Jacobian of your neural networks orthogonal to one another, then there is a possibility that you would get differential immune networks. But we don't address that question in this work. And one of the other notions that also seem interesting is that basically from an optimization perspective, what you're trying to do is you're trying to say that the defender has to not only find the probabilities, but also find the parameters theta such that you can maximize this function. So it kind of, you want to jointly optimize for differential immunity and your strategy of selection at runtime. And I don't have an answer to whether it can be done together, but seems like a very interesting notion to pursue. Now with that, let me also say that last year I have spent a decent amount of time in trying to landscaping my work that I have done over the years into these different categories. And we have a survey on moving target defense out there. And what it kind of does is it says that you can talk about moving target defenses by discussing what is that you're moving, when are you moving those, and how are you going to move that. And most of our work has kind of looked at this aspect, but we also categorize R and other works in the other categories as well. Then we also look at, if you want to consider implementing some of the MTDs in the real world, what are the kind of case studies that has been done in existing works, and what are the test beds that are available out there. And we also say that if you're considering MTDs, how do you want to evaluate its effectiveness? And then you can also go beyond just the existing security metrics, but also consider performance metrics such as latency, bandwidth, reduction, etc., in the context of moving target defense. And that kind of puts a umbrella or a landscape over the work that we have done in this thesis. Now, for the proposed work part, I'm trying to actually, ideally, maybe we should also have this arrow, trying to combine all of them and trying to address a basic limitation in the game theoretic part of our modeling. And the idea is that if you want each of these game theoretic modeling, we have somehow assumed that all these transitions are available upfront. We have also assumed that the switching cost, the impact of performance, the impact of attacks, whether they are differentially immune to the same attack or not is known upfront. And henceforth, knowing all of these parameters, we have come up with a strategy that kind of tries to randomize between choosing it for a moving target defense. Now, this is all great, but what happens in scenarios where this assumption can actually go away? And in that setting, we want to look at the notion of using multi-agent reinforcement learning. Basically, the idea is that the defender gets to interact with a simulator and provide certain deployment measures and attack measures in time. And over time, it could start off, say, something with a URS policy at time point 0. And over time, it could actually improve its policy to a more optimal one as time progresses. And this is a kind of work that we plan for new RIPS, which is due at the end of the month, or for GameSec, which is due at a later point of time, depending on when and how we get the experimental results for the paper. The timeline for my graduation and all the proposal work is kind of that I'm planning to do my proposed work over the summer, complete my thesis writing over summer and fall, and do my PhD thesis defense in fall. Besides all of this, I also wanted to highlight that I have publications in journals, conferences, and workshops. Some of these I have not actually mentioned here because those are related to NLP or other parts which I don't talk about in the thesis as much. I am also a little happy with the fact that I have been able to actually provide a code base for Markov games and Stackelberg games and Stackelberg concept solutions in Markov games, and received messages and acknowledgements across the world for actually helping people with code base for the research. So that's one of the other things. And in the case of accomplishments, I have been fortunate enough to be awarded the IBM PhD Fellowship in 2018. I think I'm the second ASU, right? Because before me, I think another person from the Browse Lab, Tagat, actually had got it. I have also been nominated for the best intern projects at Amazon Research while I was working there. And some of my work in AMAS has also been regarded as hot trends in a multi-agent community. And there have been a set of publications in AMAS 19 and 20 that extend my work and have worked on this problem of moving target defense and strategies for moving target defense. With that, I would like to conclude my proposal. Just as a small recap, I would like to say that the things that we have looked at is the use of proactive defenses in contrast to static defenses, which have to reason about movement. And instead of reasoning about this movement in a naive fashion, it's better to actually model what you know, which is known attacks against your system, and use that to your advantage in coming up with a strategy. We have also considered that how some of these defense techniques that have been used in cybersecurity can be used for machine learning or any other novel surfaces that also come into existence as time progresses. And we have said that in proposed work, we will look at addressing some of the limitations of this game theoretic modeling, which kind of is heavy on the assumption that it knows about all the rewards and the transitions of the game. With that, I would like to conclude my presentations and take questions. Thank you.
Great. So I guess now, can people hear me? I guess now we have time for questions, public questions from both the committee members as well as anybody in the audience if they want to ask any questions.
Okay, I can start with the first question.
Okay.
Hey, Sailik, this is Tiffany. So first of all, great talk. I really enjoy your proposal a lot. I have a question in terms of your applying a moving target defense and its strategy to adversarial machine learning. So if you could go to, actually, I don't know what's the page number, but it's about, the title is Crafting Attacks for Stochastic Ensemble. It's, yes, exactly. Yes, exactly, this page. So you mentioned about white box attacks and you mentioned about black box attacks. So I wonder what you mean by white box attacks and the black box attacks here in adversarial machine learning scenario. And also can I know what is the threat model or what is the like adversaries capability are you assuming in the adversarial machine learning scenario?
Right, right. I think that's a great question. So, yeah, I think I didn't mention properly what a white box or a black box attack would mean in this setting. So, the white box attack, that is conventionally the term used as white box attack in machine learning scenario, means that the attacker has access to the weights of your network, and it can use to find what different gradients are going along this network and stuff like that. It knows your network architecture model. It knows the weights on these different network architecture model. It might even know the hyperparameters that you're using if you're talking about attacks at training time and things like that. So that's like a full white box setting. A black box setting kind of says that it doesn't know about your model, but it has interaction capabilities with it, which is basically like a chosen plain text, and you can get the ciphertext for those. So basically it can choose the inputs to your system and obtain the outputs that your network might give, but it doesn't know what is the exact machine learning model that you're using. So that's the distinction between black and white box attacks and the threat models there. Yeah.
And in your setup, are you assuming that for black box attack, although attackers don't know exactly about like the model or the weight of the model, the attackers know what kind of model you're using, like whether or not you're using neural network or whether or not you're using, say, like a simple version of neural, like SVM, or very like a simple machine learning models. Are you assuming that?
Right, right. So in my case, when I'm talking about designing the game, all of these attacks that I mentioned here are essentially white box attack, which kind of says that they know, again, for vision system, the state of the art is kind of very well known to be neural networks, and even more specifically convolution neural nets, unless you have very easier classification problems like MNIST.
Yeah.
And so in that case, that assumption is kind of not a very strong one, that the attacker would know that you're using a neural network. But we take the threat model assumption much further and say that not only does the attacker know that you're using neural net model, it also knows what are the models you're using. It knows the weights of these models, and it knows that you might even be randomizing and testing. So it's a very strong attack model assumption in our case.
I see, I see. And also when you're thinking about like CN, like so you are also assuming that for the black box attack, the attackers like don't know like more specific information. For example, if it's CN, then which layer, how many layers are you using? Or you can consider like the CN with different layers as a different kind of models that the defenders is choosing between, like choosing among them, right?
So I am assuming all that. So for all of these attacks, like the fast gradient method or the PGD, the default is a little different, but yeah, sure. The default kind of can, if it knows your classification boundaries, it could still do it. But for the FGM and the PGD, you know even how many layers you're using, what are the weights of each of these individual layers. And when I discuss about the black box attack, what I'm basically saying is that this black box attack, if you were to add this black box attack as a part of the attacker's ensemble, then the rewards for this would clearly be dominated by one of these attacks in the white box. So basically the white box, which is a much stronger threat model, will be actually able to dominate any good that you might get out of black box attack. So basically you shouldn't have any incentive to use the black box attack.
Yeah, okay, that's my question, thanks.
Other questions?
Okay, so I can follow up something what Tiffany just asked. So from the practical aspect, I think in a more practical environment, if I'm the solution user, I may ask, see, I have, for example, a cloud system. I may have 1,000 virtual machines which running on multiple physical clusters. And so how exactly this black box or white box approach can help me to understand how to use them, right? So what is a connection between this like an abstract model into a realistic networking setup, considering you have a bunch of different network services and also switches to set up interconnections, which using like a private virtual lines to separate and to enable, disable some connections at different network levels?
I think that's a very good question. And I think the question at a high level kind of seeks to ask, how do you even generalize these notion of white box and black box models to settings such as cloud network scenarios or any other cyber system scenarios as well? And the answer to that is, for the works that we did in the context of cloud networks, we kind of assumed the white box attack model, which says that the defender, that the attacker knows about your cloud systems, knows about the different kind of things that are deployed in this cloud system, knows even about the different IDS systems that you can deploy in your cloud system. I understand that it's a very strong attacker threat model. And henceforth, there is this little part where I have mentioned that it could be partially observable, where you can say that the attacker has a very abstract view over the state space, whereas the defender has a much more fine-grained view over the state space in your game. But for the notions that we consider here, we assume a complete white box setting. And I think some ways, obviously, to address that would be to disassociate the same kind of representation of the state space for the attacker and the defender. You could also consider attack action, like given this new disassociated state space where the attacker has a very different view of the system versus the defender, where they're also trying to find out new stuff about the system as it goes and stuff like that. Obviously, the attack space will also change, and that will also complicate the how you find strategies in these settings. Now, one of the reasons we actually wanted to go with this kind of a formal modeling at first was because we wanted to provide an initial step for actually modeling the system in a rigorous way. And now we can allow for relaxations and see what relaxations can allow us for scalability in computational strategies versus not. And so we haven't really looked at it, but to answer your question, I think obviously for black box settings, we'll have to say the attacker considers this system as a single state right now, and after it has got entry into the system, it realizes that, oh, there is a FTP server that I can exploit, or a DB server that I can exploit, or this. And once they have reached it, they realize that I can now access a private network versus not. And it could also come up with discovery of states and actions as it progresses through the game.
But I agree. So using the white box, make your attack assumption stronger, and the corresponding security solution will be also stronger, right? So that makes sense. But practically, as I mentioned, so you may have tens of thousands of virtual machines in a cloud environments, and individually they may run in different vulnerabilities, which is hard to using a white box to realistically to emulate the entire situation. So the number of states, as you said, scalability is critical, right? And in order to using machine learning AI module, you use the data to train, that is fine. But however, if you use a game theory model to perform strategic analysis, then the state exploration problems still there, right?
Right.
And have you think about any non-optimal, maybe proximal optimal solutions, right, which is can run maybe linear or maybe polynomial time can address scalability issue to make this analysis more practical?
Okay, so right. That's a very good question. And I guess to answer the first part of it, I also want to point out that we have kind of looked at some of simulation scenarios and talked about using centralized mechanisms such as software-defined networking or SDN tools to actually scan for attacks and come up with strategies. But I also do agree with your question that even if we do this, the scalability of finding strategies becomes pretty, it's pretty unscalable if you're talking about 10,000 states and stuff like those. And so one of the ways you can think of addressing that is switching to a learning-based approach, which is kind of a part of our proposed work, where we say that we can initially start with, say, a uniform random strategy, which requires no additional effort to come up with, and then which is kind of the naive one that people generally start their MTD systems with. But as you do further interactions with the original environment, you figure out that using this strategy all the time is not actually giving you the best rewards. And then you change your strategies over time through interaction to be strategies which yield better rewards for you. So that is one way of addressing it. Now, for the case we haven't obviously looked at if there are ways to actually approximate the solution to the game setups that we have made. Obviously, one of the things that comes to mind is that ideally, if you're talking about this kind of a realistic scenario, you would have to consider partially observable games and stuff like that. And we already make one approximation assumption by formulating this as a Markov game and calculating strategies for it. So those things we have already made a little. And yet I feel that it's not as scalable. But in that case, I think starting off with what do you think are good strategies, and then over interaction, refining those, adapting it to whatever you see in the world is kind of a nice way of doing it. So yeah.
Mm-hmm. Yeah, so I think my last question will be, do you have a prototype which is available for other people to use, and how you final deliverables, so for your research work instead of research articles, do you have any practical system which is to share and people can do the evaluation by themselves?
Right. So between me and Ankur, we have quite a few code libraries available out there. One of them is the mini-net library, where you can actually set up, I won't say it's general to say that whatever network you want to set up, you can set that up, but to an extent, you can set up some of these mini-net libraries and actually models for those. And then we also have all of these libraries for Markov games and stuff like that, which could be used to calculate your strategies. So yeah, we have simulation setting code bases which could be leveraged by other people. I wouldn't say those are like real world systems. Those are like mini-net simulations and stuff like those. Yeah.
Okay, got it. Thank you.
Okay, Jijiang, you finish your questions?
Yes, I did.
Okay, so yes, here are my question. First of all, I enjoyed the presentation. It's very interesting work. I mainly have two questions here. Maybe it's due to my misunderstanding. Anyway, so I'm asking the question. The first one actually related to the slides number 61 you have right now. Suppose you derive at the current slide at a mixed strategy, which says, for example, the leftmost figure. You have 4 strategies. You're going to play 25% of each of those. What does that mean? Does that mean, for example, you have 4 strategies, A, B, C, and D.
Okay.
You play A a quarter of the time, followed by B a quarter of the time, followed by C quarter of the time, then followed by D the quarter of the time, or some other ways. So here I somehow thought there is this the timing issue in here. I do not know exactly what you mean by that mixed strategy.
Right. Okay. That's a good question, and maybe I will actually use this part to actually have this. Okay. So in the first 2 works on web application security and cloud network security and movement for those cases, we assume that we have a constant time period T, which says that after every time period T, you're going to decide that your system has to move, and you're going to use the strategy that you calculated to decide where you're going to move to. So the answer to your question as to how we play the ABCD is essentially at every time period T, you're going to roll, say, if you have 4 strategies, you're going to roll a 4-sided dice, and whichever side comes up, and this dice is a biased one, which is determined by the strategies, the mixed strategy that you've calculated, and which side comes up, you're going to say that I'm going to deploy that configuration. So let's say in the setting that you were asking, in this case, for example, in say state S0, you had these 4 actions, which was A, B, C, and D. And then in the interaction with the environment, you actually found yourself in state S0. So then you're going to roll a dice and pick one of these strategies, A, B, C, D. So for example, let's say we pick C. And then you're going to just deploy C into your environment, find out what the action the attacker executes, and then send it to the environment to get your set of rewards and states. So you're playing one at a time, and you have a fixed time period after which you have to play the strategy every time. Does that?
Okay, yeah, that answers my question. Essentially, you may be playing A, B, C, D, you may be playing A, B, D, C, but you're computing this expected utility function, right? Okay. My next question is, when defining these utility functions, you have the security concerns as well as the cost of switching. I may have missed a point. Do you consider this, you know, of the same priority, meaning you can just add those up, or one is more important than the other?
Right. So to be fair, in the work that we have looked at back in 2017, AMAS, so in that case, we consider it using an alpha, which is a tunable parameter, which says, let's say if this is 0, then you're basically saying, I don't care about the switching costs, and I only want you to maximize for security, which is given by the rewards of the defender. And if you have this, say, infinity, it says that I only care about switching costs. So, well, not infinity ideally, but a very high value, then what you're saying is I care a lot about the switching costs, and I'm fine compromising on security a little. But to be fair, I think the formulation, which now I see in retrospect, is to formulate this game as a Markov game, where you can say that your switching cost is defined by transitions from one state to the other, and your rewards in the states are defined as in the Markov game case. But for this case, we have just tunable parameters that a defender could input to actually decide what is the priority they give to switching costs versus the security concerns.
Okay, so you know, my natural thinking would be the security is of primary concern. The switching cost is a kind of a secondary, but it is also important. It's a are there any work where switching cost actually is considered in the domain in the form of a constraint? Say this, you know, say I wanted to maximize my security,
within a budget,
but the switching point is within a given tolerance.
Yeah. Right. So, okay, that's a very interesting question. Actually, I have two answers to that. One is when you're talking about switching costs, you are actually considering about only considering cost from switching from one config to the other. So let's say if you restrict it within a budget, then you could ideally say that any pairs which have a cost more than this budget, you're not going to allow for that. So basically you don't allow for those switches, which can be done using a Markov game thing where every state has a limited set of actions that you can use. So that is one way of addressing it. A secondary way of doing it is you say that it's an expected cost over time. So you say that for T steps, I don't want to exceed a budget of B in terms of switching costs. I'm not sure if anybody has looked at that, but I do see that that could be a way of considering it, where you're saying that over say X number of time periods, I don't want to exceed a cost of budget B in the switching cost parameter. But I'm not aware of any work that has looked into it.
Okay, those are all of my questions. Yeah, I'm done.
Okay. Yeah, I'm not. So is anybody not on the committee? Any of the audience have any questions? Okay, if not at this point, everybody other than the committee members and Sailik should get off the Zoom. Okay. Please. Who is Somnath Sarkar?
Hey, Somnath, I think you might want to log off.
I should be able to log him out too, right?
Oh,
So
you can kick him.
you are a co-host.
I can remove him, right?
Yeah, you can.
Just say remove. Okay, put in the waiting room. I could actually put people in the waiting room. I didn't do that. Okay, there you go. Okay, folks. So we can now, I guess, have the a session with Sailik where you can ask, okay, more. By the way, first of all, stop the recording now.
You muted.